on this computer. All right, so this is our group 303 project, deciding specifically which switch in this circuit is most efficient to check first, given that the circuit is open. So first off, we're just going to go with some intuitive options. First, with the completely super easy, straightforward option, our group wanted to say that switch 2 was the most likely to be open and therefore the most important to check first, because 0.6 is the highest probability. Therefore, we go with 2. This option obviously doesn't work because we weren't considering that the circuit was open, which means all possible combinations of independent switches 1, 2, 3, and 4, not all of them are possible. Only combinations that create an open circuit, meaning there's no direct path from A to B, will be able to be counted in the sample space because the circuit being open is given. So we then had to change the way that we intuitively look to find which switch was most likely to be open. So from here, we decided to say, let's check, let me pull up an annotation, which individual switch was included in the most combinations. So if we call 1, 1, 2, 2, 3, 3, 4, 4, then possible combinations could be 1, 2, 3, 4, 1, 3, 4, ... In the end, we found about 9 possible combos that can create an open circuit. But this method of checking which switch is in which combos include a certain switch. For example, 1 includes 1, 2, 3. Ooh, that is an awful 3. My bad. 3, 4, 1, 2, 4, 1, 2, 3, etc. had a big fatal flaw, which is even if we found the probability of the circuit being open with a switch included, we have confounding variables in each individual combo. And we have double counted instances. For example, 1, 2, 3, 4 is included 4 times. So in theory, it doesn't actually matter. 1, 2, 3, 4 being included is just adjusting the probability without giving us any real insight to which one is most likely. So this intuitive approach of seeing all the combos that include a certain switch also failed. In the end, we decided to go with excluding a certain switch. What is the expected outcome of the circuit when a switch is not included? Now, when I say expected outcome, we are instructed to consider this circuit and each individual switch like a Bernoulli's system, right? Which means the expected value, Ex, of a switch, and we'll call this switch 1, so we'll call it S1, is equal to the probability of 1. Now, this is important because these switches being independent, the ors and ands are literally just multiplying and adding. You don't have to include the intersection, subtraction, and whatnot. So when we come to excluding cases, so for example, all switches excluding 1 are 2, 3, 4. What are the other ones? Sorry.
2, 3.
2, 3,
and 2, 4.
and 2, 4, right? The expected outcome of not 1 is just going to be adding the probability of these 3 multiplied. So probability of 2 times the probability of 3, probability of 4, then probability of 2 and 3, and adding the probability of 2 and 4. And we do that for each variable. And then this, maybe not our most intuitive approach, but the third, non-mathematically rigorous approach leads us to showing that switch 4 is the most efficient switch to check, because when not including 4, the expected value of the circuit is really, really small compared to the other switches, which means using the idea of inverse probabilities, obviously we can't do inverse expected outcomes because expected outcomes aren't normalized, but in a more like reasonable sense, the deviation from the expected value of not including four was farthest from the actual outcome of the switch, which was 1. So mathematically, we'll show this here in, let me just switch this share, in this code. So we did 2 lines of code, or 2 blocks of code. One block of code is up here at the top, which defines, can you see when I highlight things?
Yep.
Cool. So it defines the probability of each switch by a decimal place, and then solves all of the individual combo expected values, because Bernoulli's shows that the expected value of any individual random variable is just its probability. So we find the expected values by just multiplying the combos. And then we find the expected outcome for each of the exclusive cases. So not 1, not 2, not 3, not 4. Then we just print those cases and try to see which one is the smallest. The smallest one would show which switch is the most impactful to keeping it open, because by not including it, we're the farthest away from the actual outcome, which is the circuit being open as provided in the problem. So here I'm going to run the top part of the code. So let me just copy this, delete it so y'all don't see it, and then we run it. And so here we see the probability of not 4 is smaller than the others by quite a bit at 0.092. And since that deviates the farthest from the outcome of the switch, outcome X is 1, EX here is 0.092 when not including 4. And since the deviation is the largest when not including 4, we decided to say that 4 is the most efficient to check. And again, that's reliant on Bernoulli's expected values equal to P. So now we come to the part where we have to simulate it. And this is pretty interesting, right? Again, with Bernoulli's, we can represent the outcome of any individual trial to be either 0 or 1. It's binary, right? Either the trial fails, and in this case, a failed trial would be the switch being closed, because the outcome we want is the circuit being open, so switches being open should be a success. And the probability of a success is just P. And so what we do is we just pretended like they're weighted coins. And to do that, we can use randoms. This is just saying, you flip a coin here, looking at this, you flip a coin, then you will get integer 1, or a success, 0.2, 0.6, 0.1, and 0.5 times respectively for each switch, being switch 1, 2, 3, 4. Then it will take those values of the randomly flipped switches and throw them through each of the test cases that can cause an open circuit. Once an open circuit is detected by checking up here in the for loop, or actually in the nested while loop of the for loop, it will stop and exit the while loop and check what values the switches hold, either 1 or 0. So if the switch is open, it has a 1. If the switch is closed, it has a 0. If the switch is open and it has a 1, a counter will add 1 and essentially say, in this trial, the switch was open. So if we run this 1,000 times, we should see the switch that's most important to check should be the switch that has the largest sum count here. So by repasting the code and running the block, we're going to run this test at first 1,000 times. And here we see that switch 4 in the 1,000-time case is the one that is open the most time.